Cluster analysis or clustering is the task of grouping a set of objects in such a way that objects in the same group are more similar to each other than to those in other groups. It is a main task of exploratory data mining, and a common technique for statistical data analysis, used in many fields, including machine learning, pattern recognition, image analysis, information retrieval, and bioinformatics. Cluster analysis itself is not one specific algorithm, but the general task to be solved. It can be achieved by various algorithms that differ significantly in their notion of what constitutes a cluster and how to efficiently find them. Popular notions of clusters include groups with small distances among the cluster members, dense areas of the data space, intervals or particular statistical distributions. Clustering can therefore be formulated as a multi-objective optimization problem. The appropriate clustering algorithm and parameter settings depend on the individual data set and intended use of the results. Cluster analysis as such is not an automatic task, but an iterative process of knowledge discovery or interactive multi-objective optimization that involves trial and failure. It will often be necessary to modify data pre-processing and model parameters until the result achieves the desired properties. Besides the term clustering, there are a number of terms with similar meanings, including automatic classification, numerical taxonomy, botryology and typological analysis. The subtle differences are often in the usage of the results. This often leads to misunderstandings between researchers coming from the fields of data mining and machine learning, since they use the same terms and often the same algorithms, but have different goals. Cluster analysis was originated in anthropology by Driver and Kroeber in 1932 and introduced to psychology by Zuburn in 1938 and Robert Tryon in 1939, and famously used by Cattell beginning in 1943 for trait theory classification in personality psychology. Definition: the notion of a cluster cannot be precisely defined, which is one of the reasons why there are so many clustering algorithms. There is a common denominator, a group of data objects. However, different researchers employ different cluster models, and for each of these cluster models again different algorithms can be given. The notion of a cluster, as found by different algorithms, varies significantly in its properties. Understanding these cluster models is key to understanding the differences between the various algorithms. Typical cluster models include connectivity models. For example, hierarchical clustering builds models based on distance connectivity. Centroid models. For example, the k-means algorithm represents each cluster by a single mean vector. Distribution models. Clusters are modeled using statistical distributions, such as multivariate normal distributions used by the expectation maximization algorithm. Density models. For example, DBSCAN and optics defines clusters as connected dense regions in the data space. Subspace models. In biclustering, clusters are modeled with both cluster members and relevant attributes. Group models. Some algorithms do not provide a refined model for their results and just provide the grouping information. Graph-based models. A clique, i.e., a subset of nodes in a graph such that every two nodes in the subset are connected by an edge, can be considered as a prototypical form of cluster. Relaxations of the complete connectivity requirement are known as quasi-cliques, as in the HCS clustering algorithm. A clustering is essentially a set of such clusters, usually containing all objects in the data set. Additionally, it may specify the relationship of the clusters to each other, for example a hierarchy of clusters embedded in each other. Clusterings can be roughly distinguished as hard clustering. Each object belongs to a cluster or not. Soft clustering. Each object belongs to each cluster to a certain degree. There are also finer distinctions possible, for example, strict partitioning clustering. Here each object belongs to exactly one cluster. Strict partitioning clustering with outliers. Objects can also belong to no cluster, and are considered outliers. Overlapping clustering. While usually a hard clustering, objects may belong to more than one cluster. Hierarchical clustering. Objects that belong to a child cluster also belong to the parent cluster. Subspace clustering. While in overlapping clustering, within a uniquely defined subspace, clusters are not expected to overlap. Algorithms. Clustering algorithms can be categorized based on their cluster model, as listed above. The following overview will only list the most prominent examples of clustering algorithms, as there are possibly over 100 published clustering algorithms. Not all provide models for their clusters and can thus not easily be categorized. An overview of algorithms explained in Wikipedia can be found in the list of statistics algorithms. There is no objectively correct clustering algorithm, but as it was noted, clustering is in the eye of the beholder. The most appropriate clustering algorithm for a particular problem often needs to be chosen experimentally, unless there is a mathematical reason to prefer one cluster model over another. It should be noted that an algorithm that is designed for one kind of model has no chance on a dataset that contains a radically different kind of model. For example, k-means cannot find non-convex clusters. Connectivity-based clustering. Connectivity-based clustering, also known as hierarchical clustering, is based on the core idea of objects being more related to nearby objects than to objects farther away. These algorithms connect objects to form clusters based on their distance. A cluster can be described largely by the maximum distance needed to connect parts of the cluster. At different distances, different clusters will form, which can be represented using a dendrogram, which explains where the common name, hierarchical clustering, comes from. These algorithms do not provide a single partitioning of the data set, but instead provide an extensive hierarchy of clusters that merge with each other at certain distances. In a dendrogram, the y-axis marks the distance at which the clusters merge, while the objects are placed along the x-axis such that the clusters don't mix. Connectivity-based clustering is a whole family of methods that differ by the way distances are computed. Apart from the usual choice of distance functions, the user also needs to decide on the linkage criterion to use. Popular choices are known as single linkage clustering, complete linkage clustering, or UPGMA. Furthermore, hierarchical clustering can be agglomerative or divisive. They are not very robust towards outliers, which will either show up as additional clusters or even cause other clusters to merge. In the general case, the complexity is for agglomerative clustering and for divisive clustering, which makes them too slow for large datasets. For some special cases, optimal efficient methods are known. SLINK for single linkage and CLINK for complete linkage clustering. In the data mining community, these methods are recognized as a theoretical foundation of cluster analysis, but often considered obsolete. They did, however, provide inspiration for many later methods such as density-based clustering. Linkage clustering examples. Single linkage on Gaussian data. At 35 clusters, the biggest cluster starts fragmenting into smaller parts, while before it was still connected to the second largest due to the single link effect. Single linkage on density-based clusters. 20 clusters extracted, most of which contain single elements, since linkage clustering does not have a notion of noise. Centroid-based clustering. In centroid-based clustering, clusters are represented by a central vector, which may not necessarily be a member of the data set. When the number of clusters is fixed to k, k-means clustering gives a formal definition as an optimization problem. Find the cluster centers and assign the objects to the nearest cluster center, such that the squared distances from the cluster are minimized. The optimization problem itself is known to be NP-hard, and thus the common approach is to search only for approximate solutions. A particularly well-known approximative method is Lloyd's algorithm, often actually referred to as k-means algorithm. It does, however, only find a local optimum, and is commonly run multiple times with different random initializations. Variations of k-means often include such optimizations as choosing the best of multiple runs, but also restricting the centroids to members of the dataset, choosing medians, choosing the initial centers less randomly, or allowing a fuzzy cluster assignment. Most k-means type algorithms require the number of clusters to be specified in advance, which is considered to be one of the biggest drawbacks of these algorithms. Furthermore, the algorithms prefer clusters of approximately similar size, as they will always assign an object to the nearest centroid. This often leads to incorrectly cut borders in between of clusters. K-means has a number of interesting theoretical properties. First, it partitions the data space into a structure known as a Voronoi diagram. Second, it is conceptually close to nearest neighbor classification, and as such is popular in machine learning. Third, it can be seen as a variation of model-based classification, and Lloyd's algorithm as a variation of the expectation maximization algorithm for this model discussed below. K-means clustering examples. K-means separates data into Voronoi cells, which assumes equal-sized clusters. K-means cannot represent density-based clusters. Distribution-based clustering. The clustering model most closely related to statistics is based on distribution models. Clusters can then easily be defined as objects belonging most likely to the same distribution. A convenient property of this approach is that this closely resembles the way artificial data sets are generated, by sampling random objects from a distribution. While the theoretical foundation of these methods is excellent, they suffer from one key problem known as overfitting. Unless constraints are put on the model complexity, a more complex model will usually be able to explain the data better, which makes choosing the appropriate model complexity inherently difficult. One prominent method is known as Gaussian mixture models. Here, the dataset is usually modeled with a fixed number of Gaussian distributions that are initialized randomly and whose parameters are iteratively optimized to fit better to the dataset. This will converge to a local optimum, so multiple runs may produce different results. In order to obtain a hard clustering, objects are often then assigned to the Gaussian distribution they most likely belong to. For soft clusterings, this is not necessary. Distribution-based clustering produces complex models for clusters that can capture correlation independence between attributes. However, these algorithms put an extra burden on the user. For many real datasets, there may be no concisely defined mathematical model. Expectation maximization clustering examples. On Gaussian distributed data, M works well, since it uses Gaussians for modeling clusters. Density-based clusters cannot be modeled using Gaussian distributions. Density-based clustering. In density-based clustering, clusters are defined as areas of higher density than the remainder of the data set. Objects in these sparse areas, that are required to separate clusters, are usually considered to be noise and border points. The most popular density-based clustering method is DBSCAN. In contrast to many newer methods, it features a well-defined cluster model called density reachability. Similar to linkage-based clustering, it is based on connecting points within certain distance thresholds. However, it only connects points that satisfy a density criterion. In the original variant defined as a minimum number of other objects within this radius. A cluster consists of all density-connected objects plus all objects that are within these objects' range. Another interesting property of DBSCAN is that its complexity is fairly low. It requires a linear number of range queries on the database, and that it will discover essentially the same results in each run. Therefore, there is no need to run it multiple times. Optics is a generalization of DBSCAN that removes the need to choose an appropriate value for the range parameter, and produces a hierarchical result related to that of linkage clustering. DLE-CLU. Density link clustering combines ideas from single linkage clustering and optics, eliminating the parameter entirely and offering performance improvements over optics by using an R3 index. The key drawback of DBSCAN and optics is that they expect some kind of density drop to detect cluster borders. Moreover, they cannot detect intrinsic cluster structures which are prevalent in the majority of real-life data. A variation of DBSCAN, NSCAN, efficiently detects such kinds of structures on datasets with, for example, overlapping Gaussian distributions, a common use case in artificial data. The cluster borders produced by these algorithms will often look arbitrary, because the cluster density decreases continuously on a dataset consisting of mixtures of Gaussians. These algorithms are nearly always outperformed by methods such as M-clustering that are able to precisely model this kind of data. Mean shift is a clustering approach where each object is moved to the densest area in its vicinity, based on kernel density estimation. Eventually, objects converge to local maxima of density. Similar to k-means clustering, these density attractors can serve as representatives for the data set. But mean shift can detect arbitrary shaped clusters similar to DBSCAN. Due to the expensive iterative procedure and density estimation, mean shift is usually slower than DBSCAN or k-means. Density-based clustering examples. Density-based clustering with DBSCAN. DBSCAN assumes clusters of similar density, and may have problems separating nearby clusters. Optics is a DBSCAN variant that handles different densities much better. Recent developments. In recent years, considerable effort has been put into improving the performance of existing algorithms. Among them are CLARANS and BIRCH. With the recent need to process larger and larger datasets, the willingness to trade semantic meaning of the generated clusters for performance has been increasing. This led to the development of pre-clustering methods such as canopy clustering, which can process huge datasets efficiently. But the resulting clusters are merely a rough pre-partitioning of the data set to then analyze the partitions with existing slower methods such as k-means clustering. Various other approaches to clustering have been tried, such as seed-based clustering. For high-dimensional data, many of the existing methods failed due to the curse of dimensionality, which renders particular distance functions problematic in high-dimensional spaces. This led to new clustering algorithms for high-dimensional data that focus on subspace clustering and correlation clustering that also looks for arbitrary rotated subspace clusters that can be modeled by giving a correlation of their attributes. Examples for such clustering algorithms are clique and SUBCLU. Ideas from density-based clustering methods have been adopted to subspace clustering and correlation clustering. Several different clustering systems based on mutual information have been proposed. One is Marina-Miller's variation of information metric, another provides hierarchical clustering. Using genetic algorithms, a wide range of different fit functions can be optimized, including mutual information. Also, message passing algorithms, a recent development in computer science and statistical physics, has led to the creation of new types of clustering algorithms. Other methods: basic sequential algorithmic scheme.